Welcome to our Electromagnetic Field Theory lecture series. In this lecture 21, we are going to discuss the first part of electromagnetic wave propagation. The objective of this lecture is to first correlate Maxwell's equations in time-varying field for wave propagation behavior, and secondly to define wave equations. Electromagnetic wave encompass a wide range of frequency spectrum, starting from low frequency noise coming from unintended sources, up to communication wave, up to wave that are considered lights, and up to wave that are considered harmful to the human body. The importance and significance of electromagnetic wave propagation is that they can be used to transport energy and information. Our analysis of electromagnetic wave are underlined by three principles. The first is the wave propagates out in all directions. Secondly, the electromagnetic wave propagates in high velocity. And finally, the electromagnetic wave follows the Maxwell's equation. Given that electromagnetic wave is propagating in all directions, we can simplify our analysis by focusing in a fixed region and looking into propagating wave that is towards a fixed direction within that particular region. We can later apply the same analysis to all the other directions. Electromagnetic wave consists of time-varying electric and magnetic fields. Supposedly, the wave is propagating along the z direction. The E field and magnetic field will have its magnitude change over time with respect to different z coordinates. Plane wave analysis refer to the analysis of electric field with respect to a plane that is perpendicular to the wave direction, as well as the analysis of magnetic field along the plane that is perpendicular to the wave direction traveling at a constant speed. To analyze electromagnetic wave, we could use the time-varying Maxwell equations consisting of these four mathematical relations. For the third Maxwell equation, the mathematical term negative dB over dt is also equivalent to negative mu dH over dt. For the fourth Maxwell equation, the term dd over dt is also equivalent to epsilon dE over dt. Having said that, we can analyze the third and the fourth Maxwell equation for time-varying field with respect to two time-varying quantities, that is E and H. For our electromagnetic wave propagation analysis, we would first begin our analysis with respect to free space medium. In a free space medium, we would assume first there is no free charge. Therefore, rho v is equivalent to 0. Given that J is equivalent to sigma E, and E is also 0 given there is no free charge, J would be also equated to 0. With that, we would modify the Maxwell equations to become as the four equations shown, with the divergence of D is equivalent to 0, and divergence of B is also equivalent to 0. The curl of E is equivalent to negative mu naught dH over dt, while the curl of H is equivalent to epsilon naught dE over dt. We would now focus our analysis based on these two Maxwell equations. The curl of a field represents a measure of how that particular field circulates a point of observation. Based on this relation, we can say that an existing electric field circulating a point of observation would result in magnetic field, the presence of magnetic field that change over time with respect to that point of observation. In this mathematical relation, we can say that the circulating magnetic field about a point of observation would result in electric field that change over time within that particular point of observation. Let's now try to visualize the deduction made from the previous Maxwell equations. Starting with an oscillating electric field, the electric field would then induce or result in the presence of magnetic field. Supposedly, we choose one point along the axis where there's magnetic field, and as a mean the field, we can say then, based on previous deduction of Maxwell equations, that electric field would be present due to that particular magnetic field. Scenarios such as this would continue to take place such that electric field and magnetic field can be said to travel along a fixed direction. This animation shows how electric field and magnetic field change over time with respect to one particular coordinate and how it travels towards a fixed direction. Electromagnetic wave would be displayed from the origin after a certain period of time. As time progresses, the displacement would also be increasing. We can therefore say that electromagnetic wave is a function of space and time. If the magnitude of the electromagnetic wave is plotted, it would demonstrate certain repeatable pattern. We could represent this mathematically using sinusoidal graph, in which the plot of the electromagnetic wave magnitude could be plotted with respect to space and time. A mathematical representation of this wave would be in this form. As electromagnetic wave travel in certain type of mediums, its energy would experience reduction as it penetrates more within that region. Therefore, we could also include this term in our wave equation. With respect to our sinusoidal graph, the time it takes to travel a certain wavelength distance lambda is equivalent to a period time of t. Lambda over t is the speed of the wave, or u, and is equivalent to f lambda. These mathematical expressions indicate there's a relation between wavelength and frequency. We will try to translate this relation in our wave equation. Supposedly, we want to represent the term inside the sign bracket with theta, an angle arbitrary on the graph. We can rearrange this mathematical relation such that z is equivalent to omega t divided by beta minus theta divided by beta. If we are to differentiate dz with dt, it would be equivalent to omega divided by beta. That is u, or the speed of the wavelength, the speed of the traveling wave. Beta is therefore equivalent to omega divided by u. Omega is 2 pi f and is also equivalent to 2 pi divided by t. U is equivalent to lambda divided by t. Beta is therefore also equivalent to 2 pi divided by lambda. Therefore, beta can be used to be related to omega divided by u and 2 pi divided by lambda, which represents relation between operating frequency and wavelength. In a free space, u is equivalent to c, or the speed of light. Let's recall back the Maxwell equations that were used in our analysis of electromagnetic wave. The curl of E is equivalent to negative mu naught dH over dt. We are now going to analyze the direction of electric field and magnetic field with respect to a traveling propagating wave. Let's suppose we have electric field in the x direction that has the magnitude change with respect to z coordinate. For Maxwell equation, the curl of E is equivalent to negative mu naught dH over dt. The curl, which employ cross product, could be solved based on this approach. From this, we can say that the E that is with respect to y direction indicate that H is also with respect to y direction, or y unit vector. If E is in the x unit vector, H is in the y unit vector, therefore E and H can be said to be orthogonal. Let's look back at our wave equation that is written in sine or cosine forms. This particular example presents the E field part of the propagating wave. The term here is the amplitude of the E field. The z here represents the direction of wave propagation with respect to Cartesian coordinate. The negative sign here indicates that the wave is moving in positive z direction. If there's a plus sign, it is indicating that wave is moving in negative z direction. The beta here is a phase constant, whereas alpha is the attenuation constant. How do we indicate the direction of electric field or magnetic field in our wave equation? Now let's consider this wave equation for electric field, and the wave is propagating in the positive z direction. Let's suppose k unit vector is the direction of wave propagation, E unit vector is the direction of electric field, and H unit vector is the direction of magnetic field. Their relations is given in these two mathematical expressions, where k unit vector crossed with E unit vector is equivalent to H unit vector. If k is z, crossed with, say for example, E unit vector in x, then H unit vector would be in y. The relation between the magnitude of electric field and magnetic field within free space is given as the square root of mu naught divided by epsilon naught, and has a value of 377 ohm. This is known as the intrinsic impedance of free space, symbolized by eta naught. Supposedly, the electromagnetic wave travel within other dielectric materials. The intrinsic impedance is given as square root of mu, or permeability of that medium, divided by its permittivity, and symbolized by eta. Let's look at one problem example. Supposedly, there's an electric field in free space given by E is equivalent to 50 cos 10 to the power of 8t plus beta x and y unit vector. We need to find or determine A, direction of wave propagation, B, the beta or phase constant, and C, the corresponding magnetic field part of this wave propagation. Solution: for part A, based on the wave equation and the plus sign plus x here, we can determine that the wave is propagating along negative x direction. To determine beta, from previous definition, that is equivalent to omega divided by c, or u, the speed of the wave within free space, we can get beta is equivalent to 0.333 radian per meter. To find corresponding H wave equation, we can use this relation to determine the magnitude of H. Given that E, the magnitude of electric field, is given as 50, the magnitude of magnetic field is given as 50 divided by 377. The unit vectors of H equation can be obtained from this relation. Propagating wave is in negative x, cross product with E, that is in y, the magnetic field would be in negative z. Therefore, the corresponding H wave equation is given as shown.